Hello everyone, welcome back to my Binary Brain YouTube channel. Today's topic is counting sort, a special sorting algorithm that works very efficiently with T-line with numbers in small range. What is counting sort? Counting sort is a non-comparison based sorting algorithm. Unlike bubble sort or quick sort, it does not compare elements with each other. Instead, it counts how many times each value appears and then uses this information to place elements into a correction position. The main idea is counting sort is very simple. Count, store, rebuild the stored array. Let's understand counting sort step by step with an example. The example array is 4, 2, 2, 8, 3, 3, 1. The step 1 is find the maximum value. First, find the largest number in the array. In our example, the maximum value is 8. The step 2 is create a count array. Now create a count array of size max plus 1. This array store how many time each number appears. Count array initially 0, 0, 0. Step 3 is count each element. Next, count how many times each number appears in the original array. After counting, 1 time is 1, 2 is 2 time, 3 is 2 time, and 4 is 1 time, 8 is 1 time. The step 4 is build the sorted array. Finally, rebuild the sorted array using the count array. The sorted output is 1, 2, 2, 3, 3, 4, 8. Why counting sort is fast? Counting sort runs in linear time or bracket n plus k bracket, where n is the number of the element and k is the range of values. This makes it faster than comparison based sorting algorithm for small range. When counting sort is used, the use cases and constraints. Counting sort is very fast, but it is not suitable for every situation. So, when exactly should we use counting sort? Let's find out. We will discuss when counting sort is used, including in real world use cases and important constraints. When should you use counting sort? The first one is when the input value have a small range. The counting sort works best when the difference between the maximum and minimum values is small. The example marks 0 to 100, age 1 to 120. In this case, counting sort is extremely fast and efficient. The second one is when the contains non-negative integers. Counting sort is designed for non-negative integers. The example exam scores, product quantities, and numbers of items. It does not work directly with decimal numbers or negative value. The third one is when fast performs in require. Counting sort runs in O bracket n plus k times, which is faster than comparison-based sorting algorithm. If speed is critical and the data range is small, counting sort is an excellent choice. The fourth one is when stability is important. Counting sort is a stable sorting algorithm. This needs element with the same value maintain the original order. The use case sorting student by marks while preserving roll number order. The fifth one is frequency based problem. Counting sort is perfect for problem where counting occurrences is important. The example is finding frequency of characters, word counting system, and inventory management. When counting sort should not be used, constraint. The first one is a large range of values. If the maximum value is very large, counting sort waste memory. In this case, comparison based sorting algorithm are better. The second one is memory constraint. Counting sort require extra memory for the count array. If memory is limited, counting sort may not be suitable. The third one is floating point of sort string data. Counting sort does not work directly with decimal number of string. The prices like then name like alias. The fourth one is sparse data. If only a few values exist in the very large range, count in sorting inefficient. Memory's count in sort is best when data range is small, values are non-negative integers, speed is important, and stability is required. The avoid count in sort when memory is large and memory is limited, data is not integer based. What if we could sort numbers without comparing them at all? That exactly the key idea behind counting sort. We will focus on the key idea behind the counting sort algorithm, the main concept that makes it fast and powerful. The core idea of counting sort is very simple. Instead of comparing element, we count how many times each value appearance. Counting sort elements by counting the frequency of each unique value and then reconstructing the sorted array using those counts. The step by step explanation. The first step is count the occurrence. First, we count how many times each number appears in the input array. Example array 3, 1, 2, 3, 2. The frequency count is 1 is 1 time, 2 is 2 time, 3 is 2 time. This step replaces comparisons with simple counting. The step 2 is store counting an array. We store these count in a separate array called the count array. Each index represents a value, and the value at that index represents its frequency. The step 3 is rebuild the stored array. Finally, we rebuild the stored array by replacing number based on its count. Sorted output is 1, 2, 2, 3, 3. Why this idea works so fast? Because counting sort avoid comparisons, it runs in linear time or bracket n plus k, where n is the number of the element and k is the range of values. This makes it faster than comparison based sorting algorithms for small range. And imagine sorting XM marks. We will discuss the assumption about the input range that counting sort depends on. The counting sort works by creating an extra array based on the input range. So if the range is too large, the algorithm becomes inefficient. The first one is input values are non-negative integers. The second one is known maximum value. The algorithm assumes we can find the maximum value in advance. The maximum value decides the size of the count array. If max value 50, count array size 51. The third one is small and limited range. The most important assumption is that the range of input value is small. The n equal 1000 elements. The range 0 to 100 efficient. If the range is much larger than the number of elements, counting sort is not suitable. The fourth one is dense data distribution. Counting sort assume that value are responsibly dense with the range. This means most value in the range actually appearing when this assumption failed. Large range. If value range from to 1 to 1000, the count error becomes very large. The waste memory and reduce efficiency. This sparse data. If only few values appear, the huge range counting sort in evasion. The negative or decimal values. Counting sort does not directly support negative numbers or floating point values. Sorting without comparing elements sound impossible, right? Let me show you how counting sort does it step by step. Okay, counting sort elements by counting how many times each value appears instead of comparing values. This step by step. The first one is take the input array. First, we start with an unsorted array. The example 4, 2, 2, 8, 3, 3, 1. Step 2 is find the maximum value. Next, find the largest value in the array. Maximum value is 8. This value tells us how large the count array should be. Then step 3, create the count array. Now create a count array of size max plus 1, the initial count array. The each index represents a number, each value represents how many times that number's appearance. The fourth one is count each element. We now scan the input array and increase the count for each value. After counting 1 is 1 time, 2 is 2 time, 3 is 2 time, 4, 8 is 1 time. Step 5 is reconstruct the sorted array. Finally, we rebuild the sorted array using the count array. For each index, we insert the number as many times as its count 1, 2, 2, 3, 3, 4, 8. Counting sort avoid comparison, which make the faster for small range. The heart of counting sort is not the input array, it's a counting array. It's understand why it needs and how it is built. Uh, Purpose of the counting array. The first one is the frequency of element. The main purpose of the counting array is to record how many times each value appears. That removes the need to compare element. The second one is enable fast sorting. Once frequencies are known, we can directly construct the sorted array. This makes counting sort run in linear time. The third one is preserve stability. When implemented correctly, the counting array helps preserve the original order, the equal element. Construction of the counting array. The first one is find the maximum value. First, to find maximum element in the input array. The maximum value is 8. The step 2 is create the counting array. Next, we create counting array size maximum value plus 1. In this case, the size is 9. Initialize with zeros. All values in the counting array are initialized to 0. This means no element have been counted yet. Step 4 is count each element. Now we scan the input array. For each number, we increase the value at the corresponding index in the counting array. Index 1, 1, 2 is 2, index 3 is 2, index 4 is 1, and index 8 is 1. Counting frequency is not enough to sort correctly, so how does counting sort know the exact position of each element? The answer is in the prefix sum, also called the cumulative count array. The prefix sum array stores the running total of counts up to each index. Instead of just knowing how many times a value appears, we now know where it should be placed in the sorted array. The prefix sum helps counting sort determine the final position of each element. It also helps maintain the stability of the sorting algorithm. The step 1 start with the count array. The first create the count array by counting frequency 4, 2, 2, 8, 3, 3, 1. The index value 1 is 1, 2 is 2, 3 is 2, 4 is 1, and 8 is 1 time. Step 2 convert count arrays to prefix sum array. Now we convert the count array into prefix sum array. Each element stores the sum of all previous count including itself. Previous sum calculation. Point 1 count 2 is 1 plus 2 equal 3. Count 3 is 2 plus 2. 3 plus 2 equal 5. Count 4 equal 5 plus 1 equal 6. Count 8 equal 7. This tells us how many elements are less than or equal to each value. Step 3. What prefix sum represent? The value at each index now represent the last position of that number in the sorted array. The example, prefix sum at index 3 is 5. So, number 3 will appear up to position 5 in sorted array. Using the prefix sum array, counting sort places element directly into their correction position. This makes the algorithm both fast and stable. Counting frequency and prefix sum are ready. Now come the most exciting part, building the sorted array. Let's do it step by step. The first one is prepare input and prefix sum. We start with the input array and prefix sum array we built earlier. Input array 4, 2, 2, 8, 3, 3, 1. And the prefix sum tells us the last position of each value in the sorted array. Step 3 initialize the output array. Create an empty array of the same size in the input array. Step 3 place element from right to left. We scan the input array from right to left to maintain stability for each element. Look up its position in the prefix sum array. The second one is place is the output array at the position. The third one is decrease the prefix sum value by 1. The fourth one is input array 4, 2, 2, 8, 3, 3, 1. Element 1 prefix sum 1 place 1 index 0. Output array 1 decrease prefix sum of 1 0. Element 3 is rightmost 3. Prefix sum 5 placed at index 4. Decrease prefix sum of 3 to 4. Element 3 left 3. Prefix sum 4 placed at index 3. Okay, then decrease prefix sum 3 to 3. Element 8. Prefix sum 7 placed at index 6. Output array. So decrease prefix sum of 8 to 6. Element 2 rightmost 2. Prefix sum 3 place at index 2. Output array 1 2 3 3 8. In decrease prefix sum 2 to 2. Element 2 left 2. The prefix sum 2 place at index 1. Output array 1 2 2 3 3 8. Decrease prefix sum 2 to 1. Element 4 prefix sum 6 place at index 5. Output array 1 2 to 3 3 4 8. Decrease prefix sum 4 to 5. Final sorted array 1 2 2 3 3 4 8. Did you know that some sorting algorithms can change the order of equal elements? Counting sort, however, is stable, and that's one of its biggest restraints. Let's see what that means. What is stability in sorting? The sorting algorithm is called stable if it preserves the relevant relative order of equal elements. The input array A3, B2, C3 and T1. First element A with value 3. Third element C with value 3. After sorting by value, a stable sort keeps A before C because they both had 3. Why counting sorting is stable? Counting sort processes the input array from right to left when built in the output array. It uses the prefix sum array to place each element in its correct position. By scanning from right to left, equal elements are placed in the output array in the same order as they appeared in the input. Step by step, the input array A with 3, B with 2, C with 3, D with 1. Count frequency prefix sum array. Place element in output array from right to left. Sorted output is table D with 1, B with 2, A with 3 and C with 3. Notice how it still comes before C even though they have the same values. We will analyze the time and space complexity of counting sort and understand why it's so efficient for creating data sets. Counting sort does not compare element. Instead, the count occurrence compute the cumulative count prefix sum, the builds the output array. The complexity depends on two things: number of element equal n, maximum value is input k. The step 1 is counting element. We first scan the input array to count frequency time equal or bracket n. Step 2, build prefix sum. We go through the count array to calculate cumulative count time equal or bracket k. Step 3, build output array. We place each element in its correct position using the prefix sum array time equal or bracket n. Total time complexity, adding all steps together or bracket n plus k. This makes counting sort faster than comparison based algorithm like quicksort or merge sort, which are o bracket o n log n for a small range of space complexity. Count array. We create a count array of size k plus 1. Output array. We also create an output array of size n. Total space complexity space equal or bracket n plus k. So count sort uses extra memory proportional to the input size and the range of value. We will discuss the advantages and limitation of the counting sort and see why it's used in some cases and avoided in other. The advantages of counting sort. The first one is fast for small range. For small range of numbers, it can be faster than comparison based sort like quick sort or merge sort. The second one is stable sorting. Counting sorting is stable. Equal element maintains the original order, which is very useful for multi-level sorting. The third one is simple concept. The algorithm is easy to understand. Count, compute prefix sum, build the output array. The fourth one is linear time complexity. For small range, counting sort effectively sort in a linear time, which is optimal for many applications. The Fifth one is useful for frequency based problem. It's excellent for problem like count words, exam marks, the inventory quantities, where frequencies. Limitation of counting sort. The first one is large range of values. If the maximum value is very large, the count array becomes huge, waste in memory and slow in performances. The second one is only works for integer. Count sort works directly only for non-negative integers. It cannot sort decimal numbers or string without modification. The third one is extra memory required. We need extra space for the count array and the output array. This can be problem for memory constrained environment. The fourth one is inefficient for sparse data. If the input has a very large range but few elements, most of the count array remain uh, empty, which is wasteful. So that's a quick overview of the advantage and limitation of the counting sort. Understanding this will help you choose the right sorting algorithm for your problem. If this video helped you, don't forget to like, share and subscribe.